So today is our continuation of lecture 9-1B. This is part 2. In part 1, we showed how to use the short circuit and open circuit test to find non-ideal practical transformer parameters. And in this lecture, lecture 9-1B, we are now going to solve that transformer circuit to find voltage regulation and efficiency. Recall that voltage regulation is Vp minus V2 prime over V2 prime, where those voltages are magnitudes, and you multiply by 100%. Also recall that for efficiency, efficiency is P out over Pn times 100%. Let's get to it. Example 2, for the following transformer, if the rated load is supplied at 0.9 lagging power factor, determine the efficiency, voltage regulation, P coil, and P core. Notice here that this is a non-ideal practical transformer that actually has the values that we derived using the short circuit and open circuit test. So we have R is 1.41, X is 4.22, RC is 2273, and XM is 1114. So the first thing we see here is that N is equal to 1 over 20, and that V2 is equal to NV1, and I1 is equal to I2. So for the first step, we are going to find I2. So I2 is equal to S over V conjugate, which is the same as the apparent power over the voltage with an angle that's negative, the arc cosine of the power factor. So that's going to equal 100K divided by 125, and the angle is negative the arc cosine of 0.9. So the current is 800 with an angle of negative 25.8 degrees. Step 2 is to find I1. I1 is equal to I2 prime, or I2 reflected to the primary side, which is the same as N times I2. So that would be 1 over 20 times 800 with an angle of negative 25.8 degrees. Which equals 40 with an angle of negative 25.8 degrees. And then step 3 is to find VP. VP is equal to 1.41 plus J 4.22 times I1 plus 2500 with an angle of 0 degrees. And that equals 2627 with an angle of 2.8 degrees. And the units are volts. For the next step, we're going to find P out. Please stop doing that. That's so annoying. For the next step, we're going to find P out. And P out is equal to the apparent power at the output times the power factor. So that's 100 kVA times 0.9. Which equals 90 kilowatts. Next, we're going to find IP, the current at the primary. So IP is going to equal I1 plus VP over RC plus VP over JXM. So that's 40 with an angle of negative 25.8 degrees plus 2627 with an angle of 2.8 degrees divided by 2273 plus 2627 with an angle of 2.8 degrees divided by J 1114. And so IP is 42.2 with an angle of negative 27.9 degrees, and the units are amps. So one way that we can find Pn is that it's the real part of VP IP conjugate, or the real part of 2627 with an angle of 2.8 degrees times 42.2 with an angle of 27.9 degrees. And that equals 95.3 kilowatts. Note that this is not the only way to solve this problem, and because the problem asks us to find P core and P coil, which is P loss, we will do that as well. So P loss is P coil plus P core. P coil is I2 prime magnitude squared times R. P core is VP squared magnitude divided by RC. So this is going to equal 40 squared times 1.41 plus 2627 squared divided by 2273. So that means that P coil is 2.256 kilowatts and P core is 3.036 kilowatts, and the total loss is 5.292 kilowatts. And so the other way to find Pn is Pn is equal to P out plus P loss, or 90 kilowatts plus 5.292 kilowatts, which equals 95.3 kilowatts. And the final step is to find the efficiency. So the efficiency, eta, is equal to P out over Pn times 100, which equals 90 divided by 95.3 times 100, which equals 94.5%. So what if we had to find the voltage regulation? The voltage regulation would be the magnitude of Vp minus the magnitude of V2 prime over V2 prime times 100. So that would be 2627 minus 2500 over 2500 times 100. So the voltage regulation is 5%. So that's right on the line of where we would want our voltage regulation to be. Example 2. A single phase load of 10 milliwatts at 0.8 power factor lagging is to be supplied at 2.5 kilovolts via distribution feeder with 0.15 plus J 0.1 ohm impedance and energy cost of 10 cents per kilowatt hour. We saw that if no transformers were used, the cost of losses was $3.285 million per year, while if 2 ideal transformers were used, the cost reduced to $1,314 per year. Now we're going to revise the savings if the transformers have the following equivalent circuit referred to the high voltage side, where R is equal to 15 ohms, X is equal to 50 ohms, RC is equal to 150 kilo ohms, and XM is equal to 100 kilo ohms. Find the voltage regulation and efficiency. Some parts are already done for you. We already had found the current before, so that doesn't change. We had done that before. Remember how we found this current? Does anybody remember how we found the current 5,000 with an angle of negative 36.9 degrees? Remember what we did before was we said I equals P over V times the power factor. We had the power, we have the voltage, and we had the power factor. And when you solve that, you get 5,000 with an angle of negative 36.9 degrees. Okay, it's labeled for you here, but that's how we did that. Then the next thing we did is we referred that current back to the feeder by using N times I load, where N is equal to 1 over 50. Where N is equal to 1 over 50. So this is 1 over 50 times 5,000 with an angle of negative 36.9 degrees. Which becomes 100 with an angle of negative 36.9 degrees. That is also already labeled on here because we've done that before. So to analyze that circuit in the middle, you can change it into the approximate circuit. Remember, for our approximate circuit, we move the parallel part to the beginning and we put everything together. So I'm going to show you the approximate circuit now. Because it's easier to analyze, that's why we do this. So the voltage source and the initial transformer is still here. Okay. And we call this V2. But then we combine all those parallel parts right here into one parallel impedance for the core. And then we combine all the series parts into one series impedance for the coil. This is the coil, and this is the core. And then over here, we now have the voltage that is going to be calculated by using the transformer formula. And none of this changes on this side. So this is still 10 megawatts, 0.8 power factor. This is still 2.5 kilovolts. And this current is still 500 with an angle of negative 36.9 degrees, okay? So nothing changes on the first and the tertiary parts. So everything changes is in the middle. The coil is the sum of all the resistors plus the sum of all the inductors. So the real part of the coil is 15 plus 15 plus 0.15. So this is going to be 30.15 ohms. Remember, this is an approximation. We know they're not really in series, all right? Okay. Then you add up all the imaginary parts. It's going to be 50 plus 50.1 plus 0.1. So this is J 100.1 ohms. And then to find the parallel parts, you put them in parallel. So 150 in parallel with 150 is 75. So this resistor becomes 75 kilo ohms. This resistor becomes 75 kilo ohms. And the inductor becomes 100 in parallel with 100, which is 50. So that becomes J 50 kilo ohms, okay? 75 kilo ohms for the resistor, J 50 kilo ohms here. And the voltage here we know is 125 with an angle of 0 degrees kilovolts. Because we know you divide that by 50. And we know that this current here is 100 with an angle of negative 36.9 degrees. All right, so what we need to find next is V2. We need to find V2. How can I find V2? It's going to be that feeder impedance times what I'm going to call I2. So that's going to be 30.15 plus J 100.1 times 100 with an angle of negative 36.9 degrees. V2 is going to be the voltage drop across the feeder plus 125 kilovolts. The voltage across here plus the voltage across there gives me V2. So when I do the calculation for that, I get 133.56 with an angle of 2.66 degrees in kilovolts. The power loss in the coil is going to be the magnitude of the current times 30.15. What's the magnitude of the current? The magnitude of the current is 100. So it's going to be 100 squared times 30.15. Then we need VP squared over the values of this, which is 75K. So that's going to be, what is VP? What is VP? VP, according to our formula, would be the same as V2 here, right? So it'd be the magnitude of V2, which is 133.56. 133.56 squared, okay? Find P loss, please. Find P loss. 539.5 kilowatts. So the efficiency is P out over Pn. So what are those values? P out over Pn. So we go back to our formula. The formula was P out over Pn is the same as P out over P out plus P loss. Yeah, it is. Thank you, Miguel. Sorry, this is K squared. Thank you. Sorry. Is that what was wrong with it, Noah? Yeah. Sorry about that. That should have been K squared. This is kilovolts. Try it again now, Miguel, and see if you get it. That numerator should have been 135.56K. What about now? Okay, sorry about that. So the efficiency is P out over Pn, or P out over P out plus P loss. We know what P out is. That's given in the problem statement. It's 10 meg. So this is 10 meg over 10 meg plus 539.5K times 100, 94.9%, okay? So what I was going back through our notes and I was trying to find where we did this problem previously. Ideally, what we should see is that by adding these transformers, we should improve the voltage regulation and the efficiency. So I was trying to find where we did this problem before and compare what we had. But I'll just tell you, what you should see is that the efficiency and the voltage regulation improve.